Hi everyone. So today we are first going to discuss what does it mean to say when two lines are parallel. After that we'll discuss the various avatars of parallelograms. And finally we're going to expose hidden parallelograms in the midpoint theorem configuration. So let's go. We want to talk about parallel lines, parallelograms and midpoint theorem today. So let's start with what are parallel lines. Parallel lines are lines that don't meet at all. That is the most common thing we hear about parallel lines, and it's like known to everyone, right? Now, this definition of lines that don't meet at all is not very scientific because, in some sense, if somebody gives you two line segments and asks you whether they are parallel, like these two, then how will you check whether they are parallel or not? You'll have to extend it, and you have to keep extending it all the way, right? So, and who knows, if it's slightly tilted, these lines may meet very, very, very far away. So one needs a local criteria one can use locally and measure. You draw a line cutting these two parallel lines called a transversal, and then you measure these two angles, okay? Measure these two angles the parallel lines makes with the transversal. If these two angles add up to 180, or in other words, if these two angles are supplementary, this condition, then we can say that the lines are in fact parallel, okay? Now, notice that the word supplementary is also related to the linear pair. That is, if you draw a line and another line segment meeting here, then the angle sum here, the sum of these two angles is again 180. Okay? So generally, this is called a linear pair. So with these two put together, we basically get a nice array of equalities. So given two parallel lines, here the black lines, and a transversal, a pink line that I have drawn here, all these four angles are equal. Okay, the angles above are called corresponding angles. Okay, and which are the angles on the same side of the line. If you consider angles on different sides of the line, that is, for instance, this angle and this angle, then we call them alternate angles. Okay, so even alternate angles are equal and corresponding angles are equal. Even the converse is true. If the corresponding angles are equal for two lines and a transversal, then these two lines are parallel. Okay, and if the alternate angles are equal also, the two lines are parallel. So you can detect parallel lines by checking whether these two angles are supplementary, or whether alternate angles are equal or corresponding angles are equal. Okay, so these are the various ways in which one can detect parallel lines. All right, so we move on to now parallelograms. Okay, now parallelograms have different avatars in the sense that one can talk about parallelograms in various ways. One of the ways you can find a parallelogram in the wild is when you have two sets of parallel lines, intersecting. So in this case, as you can see. So when you have two sets of parallel lines intersecting, the bounding quadrilateral is a parallelogram, and this can be easily stated as a quadrilateral whose opposite sides are parallel. On the other hand, you can have a quadrilateral in which opposite sides are equal. As you can see, the red colored sides are equal and the green colored sides are equal. So even in that case, it's a parallelogram. So if you know that a quadrilateral has opposite sides equal, then it's again a parallelogram. Now you have somewhat of a mix between the two, a condition between, right? That is, if you have a quadrilateral in which one set of opposite sides, you see the dark line here, one set of opposite sides are equal and parallel, then again it's a parallelogram. Now we know that once these lines are parallel, we already learned about parallel lines just now, and this was here, we already learned that these two angles are supplementary, which means that in a parallelogram, these two angles are supplementary because these are parallel lines. Okay, so since these are parallel lines, these are supplementary, but these are also parallel lines, so these are also supplementary. Okay, so which means that when you have a parallelogram, adjacent angles are supplementary. Now, the fact that adjacent supplementary angles are unique tells us that this particular angle is supplementary to this angle, and this angle is also supplementary to this angle, forcing these two angles to be equal. So you can define parallelograms in yet another way. You could say that a parallelogram is a quadrilateral in which opposite angles are equal. Okay. Now, there is another way to detect a parallelogram, and it's a very interesting one. If you have two diagonals bisecting each other in a quadrilateral, then that quadrilateral must be a parallelogram. So how do you find this in the wild? The way you find it in the wild is that supposing you have a stick or some line segment somewhere in the plane, or maybe a stick or a wire, and you have another stick or a wire cutting it in such a way that both of them have a common midpoint. The green and the blue segments both have a common midpoint, then that is as good as saying these two lines bisect each other. Then the outer quadrilateral becomes a parallelogram. Okay, you can just rotate it even, it doesn't really matter, it will always remain a parallelogram, the outer quadrilateral. So that's what this is saying. Okay, and finally you have some kind of a cross between the two, the condition here. Okay, which is saying, supposing you have one set of opposite sides parallel and one diagonal bisects another, even then you have a parallelogram. Okay, so these are like 7 different ways of thinking about a parallelogram: 1, 2, 3, 4, 5, 6, and 7. So we are going to basically prove the midpoint theorem, okay, using parallelograms. Now let's understand what the midpoint theorem is. The midpoint theorem states that if you have a triangle ABC, if you mark the midpoint M of AB, the segment AB, midpoint means AM is equal to BM. Okay. Secondly, supposing you mark the midpoint N of AC, then if you join MN, then this MN is parallel to BC, and this MN is the length, is half of the length of BC. Okay, so that's what it says. So let's write it out. Okay, so now how do you prove this theorem? Notice that here, if you look at it very carefully at this point, you see that this length and this length are equal. Okay, these two lengths are equal, and it almost looks like one of the configurations of the parallelogram where there's a line cutting and there's already one that is bisecting. Okay, so if you look at this, one diagonal bisects another diagonal, right? So there's another one here as well. There are 2 of them, but let's use this one. So if you compare here, notice that this blue color line is like this thing, is already bisecting, and this green color line here essentially is like this pink line, but it's only halfway through. So to make it into this configuration, convert this diagram into this one, all I had to do is extend MN out here. Extend Mn to x such that n is the midpoint of mx. Now you see you are exactly in this situation. The diagonals bisecting each other, then we know that the outer bounding quadrilateral is a parallelogram. AX and CX are equal and they are parallel. Okay, so let's write that. So what do we know? So we have CX is equal to AM and it is parallel to AM. But wait a minute, AM is equal to MB. Okay, AM is equal to MB. So CX must equal MB as well. Further, CX is parallel to AM, but AM is essentially this line. The part is a segment of this line. So essentially CX is also parallel to BM. Now, what does that mean? Well, this means in the quadrilateral MXCB, you have one set of opposite sides parallel and equal. And remember, that was one of the definitions of a parallelogram. If you have one set of opposite sides equal and parallel, then that's again a parallelogram, right? So you have one set of opposite sides equal and parallel. That's what we proved. All put together, we have something very interesting. Now, MXCB is a parallelogram, which means opposite sides are again equal and parallel. We can conclude MX is parallel to BC and MX is equal to BC. But wait a minute. N is the midpoint of MX. So MX is also 2 times MN. Both put together, since MX is both 2 times MN and BC. Notice MX is equal to BC because MXCB is a parallelogram. Okay, just recalling. So BC must equal 2MN. Okay, BC must equal 2MN from here, it implies. Further, MX is parallel to BC. Since M and X are collinear, this implies MN is parallel to BC. And there we go, we are done. Because what we had to show was MN is parallel to BC and BC is 2 times MN.
Now that we have seen the midpoint theorem, in the next few videos we will see its powerful applications.